Systems thinking is a really important skill for testers. Now, the concept of systems might already be known to you. Of course, you might be involved in testing a system right now. But there's a more general view of what systems are. We don't just test software or products or applications. We test systems. Now, systems or systemic thinking is required in every case. So we need to know, firstly, what is a system? A system is a group of interacting, interrelated, or interdependent parts that form a complex and unified whole that has a specific purpose. Now, that's a rather long-winded kind of definition, but it has all the components, if you like, that make up what we understand as a system. Let me give you some examples. So, for example, a football team is a system. It has players. You might call the players components of the team. But that team of players is supported by a coach and all the backroom staff and the organisation within the context of the football club in its entirety as an organisation. An electric toaster is a system. It has mechanical parts, it has electronic parts, it probably has a bit of software in it nowadays. An airport is a massive system of systems. There are many computer systems there, of course, but there are the buildings, the baggage handling system, all the hardware and mechanical aspects of that, all the trucks that service the planes as they arrive and depart, and so on. It's a massively complex system. The National Health Service, whichever country you're in, is a humongous organisational system. The human body is a system, and we're still struggling to understand how it works. It's way beyond the complexity of any one individual to understand. An aircraft carrier is a system. Like an airport, it's a super system. It's a system of systems, and there might be 1,000 or multiple thousand systems in an aircraft carrier. Now, the point of this is to say that it's parts that coordinate, collaborate, interact to deliver some purpose, to achieve some goal, if you like, for the system as a whole. Without the interdependencies of the parts, you just have a collection of parts. You don't have a system. So let me differentiate systems from a collection of parts. In a system, two or more parts interact as a whole within some kind of contextual boundary, some scope, if you like. A collection is just a group of parts that don't interact. In a system, the behaviour of that system changes if you change a part or if you remove a part from that whole. In a collection, the parts don't interact, so taking one part away doesn't change anything except you've got fewer parts. Now, systems critically have a purpose or a goal, an objective, if you like. The purpose of the system is a property of the system as a whole. The parts of the system don't have the same purpose, if that makes sense. All parts of the system are required to make the system work, if you like. If you take a wrench out of the toolbox doesn't change, it's just you've not got the wrench in the toolbox anymore. If you change the wiring of a TV set, clearly the TV set will behave differently. Systems maintain stability through feedback. These are interactions between parts within the system as a whole. So toasters have a thermostat which tells it to switch off when the temperature is reached. Teams talk on the field of play. The coach on the sideline gives advice as he witnesses the game in play. Interconnected systems communicate through messaging and responses. Now, the importance of a system having a purpose is critical. So let me talk at like two extremes. So with mechanical systems, we could say a car is a means of travel. That's its purpose, to transport people from one place to another. An electric tumble dryer dries wet clothes. A vacuum cleaner removes dust and debris from carpets and floors and so on. And the clue is often in the name of these mechanical systems. But what is the purpose of a bacteria, or a worm, or a chimpanzee? These are biological systems, the most complex things we know of, really. They can change their purpose over time. They evolve, literally they evolve. We can never be sure what their purpose is often, because if human systems, if they're sentient beings, have free will and they decide what they do and what their goal is in life. This is why living systems are so difficult to understand. Software systems are somewhere in between the mechanical and the biological, the natural, if you like. Now, to illustrate this, this idea of emergent properties, the evolution of systems, if you like, that change over time. A trivial example would be if you look at the hydrogen and oxygen atoms that make up a molecule of water. Hydrogen is a gas. Oxygen is a gas. But water at room temperature is a liquid. Now, how do you get a liquid from gases? It's an emergent property. Of course, when you ignite hydrogen and oxygen, if they were mixed together, you get a flame or an explosion. But what remains is some energy generated and liquid water when it settles down to room temperature. So the liquid versus gaseous states is an emergent property. Okay, you can't get that emergent property, the liquid, from hydrogen or oxygen alone, or even when you mix them at room temperature. Now compare this idea of parts versus systems with sports teams, soccer, baseball, rugby, whatever. Suppose you picked a team of all-stars, of world-beating players, and put them against the best team in the world. Who would win? Now, I'm being kind of crude here in that there's currently a situation with Manchester United and Liverpool. Manchester United are kind of in disarray, and Liverpool are the best team they've ever been. So it's very obvious that the system at Manchester United is not working, and the system at Liverpool is working very well. So, if you like, the United team are a group of individuals, parts, let's say, whereas the team system within Liverpool clearly is a set of patterns to which the players adhere. And so that's why they're being so successful right now. In the next video, I'll talk about systems thinking and how this idea of systems helps you to test.